Hi everyone, so in the last video we were looking at Newton's theory of gravity and the equations that are involved in Newton's theory of gravity. And the ultimate equation that we came to was Poisson's equation. And I said that really that one equation sums up all of Newtonian gravity. So it's an equation relating the mass distribution that generates the gravitational field, and it relates it to the gravitational potential phi. So it's like someone gives you a mass distribution with a certain mass density, and Poisson's equation tells you here's how you find the gravitational potential. It's a second order linear differential equation, and if you can solve it, then you've got that potential phi. You can use it to find the gravitational field, and from there you can use Newton's second law to find how particles like planets and asteroids or whatever you like will move in that gravitational field. And we moved on then to think about Einstein's theory of gravity and how the equation, the one equation that we can use to describe Einstein's theory, how it will look in general shape, okay? And we said it's going to look like this. So on one side, we're going to have a tensor describing the mass or energy distribution that generates the so-called gravitational field. Okay, so this really takes the role that the mass density had in Newtonian gravity. And on the other side then, we will have a tensor describing the curvature of space-time. Okay, and remember we said that this is the metric theory of gravitation. This is how Einstein says gravity works. When you have massive objects like stars and planets, just the presence of mass curves the space-time. And so that's why we have an equation like this. On one side, something about the mass, and on the other side, something about the curvature. And I said that ultimately, when we go to solve this equation, what we will be trying to solve for is the metric tensor that describes the curved space-time. So in Newton's theory, you solve for the potential. In Einstein's theory, you solve for the metric tensor. Okay, they are like a one-to-one relationship, really. Okay, so the metric tensor now takes on the role that the gravitational potential had before. Okay, so we're just going to now take a look really at the details of what these tensors are. Okay, so we're going to start with this side, the tensor describing the mass-energy distribution. And this tensor is actually called the energy momentum tensor. You've actually already seen it with Dermot when you looked at electromagnetism. You've seen it in a slightly different form. So, what is it? It's a tensor, as I say, that describes the mass or energy distribution. So imagine you just have some blob of mass, okay? And this is your mass in space that is generating the so-called gravitational field, okay? That's generating the curvature of the space-time really now. And let's suppose, okay, we have an origin somewhere, and let's suppose then that we can just pick some point, okay, inside that mass distribution. And at that point, there will be a mass density, okay, so there will be a certain amount of mass at that one point. So if we choose the rest frame at that point, okay, why did I say about choosing rest frame? Because this mass distribution may not be static, okay, it could be moving, could be flowing, could be doing anything really. So think of it in totally general terms as just a mass distribution, and you know, it can be it's like a fluid really, okay, so it can just be moving. So at any particular point there is a mass density, and let's choose though the rest frame at that point. Okay, so even if the mass is actually flowing at that point, let's just switch to the rest frame at that point. And remember that locally we can choose an inertial frame, so it's okay to do that. So choose the rest frame and call the mass density at that point rho 0. Okay, so rho 0, mass density in rest frame. The amount of mass at that point. And how is the energy momentum tensor then defined? It's defined like this. So T, we call it capital T, and it's got two indices, and we'll put them upstairs, contravariant form. Okay, so T mu nu is equal to rho 0 V mu V nu. Okay, so v mu and v nu here are the 4 velocity of the matter or the mass at this point, okay? So I know I said a second ago that it was it's the rest frame, but there are 2 frames of reference in discussion here, okay? So the first frame of reference is where I just look at the mass distribution as a whole, and I have this origin outside, and so it's like a fluid, and everywhere it could be flowing, okay? The mass could be moving, okay? So at any particular point, you've got a 4 velocity, but if you pick one particular point, then you can pick a rest frame at that one point and find the mass density there, and that's rho 0, okay? So this is the energy momentum tensor. This is how it's defined, okay? So v mu and v nu here are the 4 velocity of the matter at any one point. And remember from what you saw in special relativity that the 4 velocity is as follows. So v mu is equal to gamma, so the Lorentz factor, and with your speed v, and then you have c, comma, and then the 3 vector v, okay, the 3 velocity. Now, that's it, okay? So I'm not going to get into a massive amount of discussion here, but suffice it to say that this tensor describes everything that you need to know about the mass distribution, okay? At the end of the day, basically what we need to know is, at each point in space, how much mass is there, and then which direction is it moving with which speed. That completely characterizes the mass distribution, okay? So you just need to know how much mass is there at this point and where is it going, okay? What's the 4 velocity, basically, and what speed is it going at. Now, in your PDF notes online, what we will do there is have quite a detailed discussion of what the individual components here all mean. Okay, so there's a physical interpretation for each component. So remember here, with the Greek indices, this means the coordinates x0, x1, x2, x3, okay? So that convention we carry over from special relativity, okay? And x0 is just c times t, where t is the time. So that's the same, the 4 coordinates of space-time. So mu and nu here can take 4 values each. So this is a rank 2 tensor, so that means it's got 4 times 4 components. So 16 components here in all. So in the notes, I will discuss what each component means. There's a physical interpretation for each. But to be perfectly honest, in the applications that we're going to be looking at, we're going to be thinking about quite simple systems, okay, very simple. We're going to be thinking about, you know, the so-called gravitational field produced by like a star, for example, you know, so you might have the sun and then you've got other particles like planets moving in that gravitational field. So in a simple case like that, you don't even have to worry about all these 4 velocities and so on, because you can just think of your star as just being static. Okay, so in the applications we're going to have, it's just going to be a static mass distribution, okay, there's no movement in it. And in that case, actually only the 0th component of the energy momentum tensor is non-zero. Okay, so if your mass density that generates the gravitational field, if it's static, then you see that 3 velocity is 0 at every point. And that will be the case in our applications. So the only non-zero component then is t00, which, as I say here, is rho naught, and it'll just be v0 times v0, and you can get that from here. So v naught is just gamma c, so you'll just have gamma squared v, c squared, but v is 0, okay, so I should really just put 0 there, and gamma of 0 is just 1, so this is just rho naught c squared. So this is really just actually energy density. Okay, that's what this component is. Okay, so T00 describes the energy density at your point in question, because it's like, you know, it's like E equals mc squared. Okay, this is the same thing. So you've got c squared there, and then here you've got mass, here you've got mass density. So this is energy density. Okay, so it's like how much energy is there really at this point. So at any rate, in most general terms, that's the tensor here on this side of the equations of general relativity. Okay, so for a more general flow where it is moving in general, the energy momentum tensor is given by this. And a couple of important properties before we go any further. So I'll just say properties of this energy momentum tensor. First of all, and hopefully it's quite obvious, it's rank 2, okay? So 2 indices, it's rank 2. It's also symmetric. Okay, so look, if you interchanged mu and nu, then you just interchange them here. But, you know, it's just v mu times v nu, or v nu times v mu, doesn't matter. It's symmetric, whichever way around you write it. It's also divergenceless, okay? What does that mean? Think back to the last chapter where we defined the divergence of a vector field. How do you do that? You take a covariant derivative of the vector. So imagine, forget about the energy momentum tensor for a second. Just think about a vector field. If it's divergenceless, what does that mean? It means you take this thing, so this would be the divergence of a vector t, right? Remember that? So it's covariant derivative with respect to x mu times t mu. So you take a sum over mu. That's how we had divergence in the last chapter. Here, however, it's not a vector, but a rank 2 tensor. So there are actually 2 different divergences. Okay, so there's a divergence where it's the sum over the first index, and then there's a different divergence in principle where it's the sum over the second index. So there's a different divergence where you have nabla t nu. So you have nabla nu t mu nu, summing over the second index. But they are both the same actually in this case because it's a symmetric tensor. Okay, so you switch those 2 indices, it's no different. So at any rate, the energy momentum tensor is divergenceless. Okay, and what does that mean? Physically, it means conservation of energy and momentum, basically. Okay, that's really all I want to say about the energy momentum tensor. Okay, so in general terms, it's like this, but for our purposes, where we're looking at static mass distributions, so like maybe the gravitational field produced by it as just a star that's just at rest, then only the 0, 0 component is non-zero. Okay, so really it just goes back to being the mass density times a factor c squared. Now, let's get to this other side then. So now that we've looked at the tensor describing the mass energy distribution, let's think about the tensor that describes the curved space-time and what that can be. Well, think back to our previous chapter. Think back. We had something called the curvature tensor. Remember that? And it told us an if and only if condition for a space to be curved. Remember, a space is Euclidean. Okay, so the space is flat if the curvature tensor is 0 everywhere. Sorry. Okay, so if the curvature tensor is 0 everywhere, the space is Euclidean. So, could this be the curvature tensor? No, it couldn't. Okay, why not? Because you see the left and right hand sides of this equation. Okay, these tensors will have to have the same properties. Okay, so because this is an equation between tensors, they will have to have the same properties. Okay, so for example, whatever this tensor is over here, it will have to be rank 2, and the curvature tensor isn't. Okay, the curvature tensor was rank 4. Remember that? Okay, so the curvature tensor was like R, I, J, K, L. Okay, so that won't do. Can we think of any rank 2 tensors that we saw that were related to the curvature tensor? Oh yeah, we can. We had the Ricci tensor. Remember it? So the Ricci tensor was rank 2, so it was just Rij. And we found it from the curvature tensor by contracting the first and last indices. So could it be the Ricci tensor that goes here? Well, is it rank 2? Yes. Is it symmetric? Yes, it actually is. We proved that, okay, in one of the videos in the last chapter. So the Ricci tensor would satisfy that and that. Is it divergenceless? No, it's not actually, okay? I didn't show that in the videos, but I do show it in the lecture notes, at least at the end of the previous chapter. So the Ricci tensor satisfies this and this, but not this. So it won't work either. Okay, what can we do? Well, here's what we're going to do. Whatever this tensor is over here, the tensor describing the curvature of space-time that has to satisfy these three properties, I'm going to call it G mu nu. And it turns out that you can choose it as follows. R mu nu minus a half G mu nu R. You can choose it like that, where what's what here? This is the Ricci tensor, written in contravariant form, albeit, but that's okay. G mu nu here, that's the metric tensor in contravariant form. And R here is the Ricci scalar, okay, which remember was found from the Ricci tensor by putting it in mixed form and contracting two indices. So it turns out that this is the answer. Okay, so this particular combination, which I now call G mu nu, and there's a special name for this, we call it the Einstein tensor. It satisfies these three properties. It's rank 2, for sure. Yeah, there's two indices. Fine. It's symmetric. Why is that? Because the Ricci tensor is symmetric and the metric tensor is symmetric. And it turns out it also is divergenceless. Okay, there's a proof of that in the online notes at the end of the previous chapter. So it is at least a candidate for what could go over here. Okay, yeah, it satisfies these three properties. So, maybe the left-hand side here could be this. But that's not really a proof, okay? There are other combinations of tensors you could come up with that work and satisfy these three properties. And it sort of feels like we've just plucked that out of thin air. Okay, so, you just take this kind of arbitrary combination and it just happens to satisfy the three properties. And we say, right, well then maybe that'll do over here. So it doesn't really feel like we've derived that from first principles. That's right. Okay, it's just a guess. And that's all it is. Okay, you can't prove that this is right. But this is what Einstein's theory postulates. It postulates that this is how gravity works. It just takes this combination and says, maybe this is it. I can't prove it, but maybe it is. And if it agrees with experiments and stuff that we can do, then happy days. But, ultimately it may be wrong. To this date, no one has found anything, no one has found any experimental evidence that contradicts general relativity. But it is just a postulate and nothing more. But at any rate then, we have our two sides. So that gives us then this equation now written properly, and it's called Einstein's field equations, okay? The equation of general relativity. So Einstein's field equations. Okay, and I'll write them here again. So on the left-hand side, you've got this Einstein tensor, so it's R mu nu minus a half G mu nu R equals, now on the right-hand side, it's the energy momentum tensor. But I suppose there is one sort of extra part of the postulate. Rather than saying them just equal like that, and that's it, possibly, there's rather than them just being equal, maybe there's a constant of proportionality. So maybe there's a constant here, which we'll call it minus kappa. I think that's the way I've called it in the notes. It's just a constant of proportionality, which again we can determine by experiment or something, but we'll get onto that constant maybe in the next video. So that's it. That's Einstein's field equations there. That is the big equation of general relativity. Okay, you can also write it in, it's written in contravariant form here, but you can have it in covariant form or even in mixed form. So you can lower the indices all the way across, like this. Or you can also have it in mixed form, so you can have R mu nu minus a half. Now remember, there's no such thing as a mixed metric tensor. If you take the top form and lower indices all the way across, so how do you do that? Multiply through by a covariant metric tensor, it will be the matrix inverse of this contravariant metric tensor. So what you'll actually you'll get in the end is a delta mu nu r equals minus kappa T mu nu. So there we are. That is the equations. These are the equations of general relativity in 3 different forms. And again, what's the goal? Okay, it looks very abstract, right? All these tensors. What do you try to do in practice? What's the goal here? So someone gives me a distribution of mass or energy. Okay, so they give me, in other words, the energy momentum tensor that describes it. Okay, so maybe it's static, and in which case then there's only the 0, 0 component to worry about. Okay, maybe it's not, maybe it's flowing, maybe it's moving. Then you have other components too. But at any rate, someone gives me the distribution of mass that generates the so-called gravitational field. In other words, they give me T mu nu. They give me the energy momentum tensor. What do we try to solve for over here? Well, we put our energy momentum tensor here. So what are we trying to find over here? Well, remember way back. Okay, so you've got the Ricci tensor here. Okay, here it's up here. The Ricci tensor, you've got the metric tensor, you've got the Ricci scalar. But all of these 3 things relate back ultimately to the metric tensor itself. Okay, so remember, the Ricci tensor, what is that? It's a rank 2 tensor, but it's a contraction of the curvature tensor. Okay, so remember, just as an aside, R, if it's written in covariant form, R mu nu, it's just, you take the curvature tensor and you have the first index and last index set equal. So I can put a dummy index there, lambda. That's the curvature tensor. Okay, but how is the curvature tensor defined? I don't want to write it all out again, but it's defined in terms of Christoffel symbols and their derivatives. Okay, that's what's in there. Okay, that's what's in the curvature tensor. And what's in the Christoffel symbols? How do you get those? From the metric tensor. Remember method 2 of finding Christoffel symbols? By taking derivatives of the metric tensor. So the Christoffel symbols themselves come from the metric tensor and its derivatives. Okay, so that's what's ultimately in there in the Ricci tensor. It's just a contraction of the curvature tensor. It's built up from Christoffel symbols and their derivatives, which in turn are built up from the metric tensor and its derivatives. And similarly for the Ricci scalar. Okay, the Ricci scalar is just the contraction of the Ricci tensor. And so what are we trying to solve these equations for? For the metric tensor components, ultimately. And in fact, remember Poisson's equation? Okay, so in Newtonian gravity, you had Poisson's equation, which I can maybe fit here. So I'll just say CF, which means compare, with Poisson's equation, nabla squared phi equals 4 pi g rho. Remember, in Newtonian gravity, someone gives you the mass density and you're trying to find phi. And this is a second order differential equation. That's important, okay? So, second order differential equation. This Einstein's field equations, although it doesn't look like it, it is a second order differential equation for the components of the metric tensor. How so? How is that? Because to get the Ricci tensor and also the Ricci scalar, you take the metric tensor and its derivatives and you find Christoffel symbols. Okay, and what do you have to do in the Christoffel symbols? You have to differentiate the metric tensor. Okay, so you've got the metric tensor and its derivatives in the Christoffel symbols, but then to get the curvature tensor, you have to differentiate the Christoffel symbols. So you end up with second order derivatives of the metric tensor components. So that's how that happens. So this is a second order differential equation for the metric tensor. It's not linear anymore. They're not linear differential equations like here, so very difficult to solve, can only be solved exactly in a few very, very elementary applications, okay? But that's what we're going to be looking at next, okay? So well, we have a little bit more to do about the equations themselves, but that's ultimately what we're going to be focusing on in this chapter. So a couple of particular solutions of these. Okay, so trying to find the metric tensor. And by the way here, how many equations are there to solve? Okay, so remember over here in Newton's theory, there's just one equation. Okay, everything's scalar, so there's just the mass density, and there's just a gravitational potential, that's it. But here, these are rank 2 tensors. Okay, so it's 4-dimensional space-time, so that's 4 times 4, which is 16. So there are really 16 equations here to be solved, but symmetric. Okay, so not really 16, there are actually only 10 independent ones. Okay, because if you think about a 4x4 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, if it's symmetric, that, and that, you need to find that, and that, and that. Okay, so 10 independent components. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 3, these 2, and this 1 are found just from the summary. So there are 10 equations here, so 10 independent components of the metric tensor to be found. Okay, so really, it's like there are 10 gravitational potentials in principle here. Okay, so it's just an analogy, okay, between the metric tensor and the potential. And also then, once you have the metric tensor, and with this I finish, once you have the metric tensor, so the potential, so to speak, then the gravitational field, where does it come from? The gravitational field, remember, well, the potential is the gradient, the gravitational field is the gradient of the potential, and it's the same thing here. So in Einstein's theory, whatever replaces the gravitational field will be the derivatives of the metric tensor, which is the Christoffel symbols. Okay, so remember, Christoffel symbols are found by differentiating the metric tensor, and that's why the gravitational field can change depending on your reference frame, because Christoffel symbols are not tensors. They can even be made to disappear by an appropriate change of coordinates at a single point. Okay, I've talked enough. This is Einstein's field equations. In the next video, we'll look at some more properties, what this constant is, and we'll go from there.